And this, of course, that's the Earth. That's where we live. The bottom of that image is what's important. This is just from 2019. And at the bottom of the picture, you see a graph. On the right, it shows the temperature. And it shows that since 1900, the average temperature of the Earth, and that includes air, water, and land, the average temperature has risen 2 degrees, which by itself doesn't sound like a big deal. But it also shows, the legend at the bottom shows that this is data that's coming from multiple sources, multiple countries. So the first thing is there is no debate whatsoever that the Earth is warming. There is no debate. A lot of people say, well, how do you know what it was in the past? We weren't here. We didn't have satellites. We didn't have data. We didn't have electricity. Well, we use something called a proxy. And one of the best proxies is, let's bring this up for you. It's ice cores. So right in this is a web page from NASA. And ice from glaciers does not melt, or at least it didn't really melt much. But if you drill a core of ice, you drill straight down, the deeper you dig, the farther back in time, we're talking hundreds of thousands of years of data. You take the ice to a lab, and in the air bubbles, you get the actual air that existed 100,000 years ago. It is trapped in the air bubbles. Another way we know is using sediment cores. And this has been done at Lake Shelby. Same thing, you dig Lake Shelby in Baldwin County by Gulf Shores. You dig down, you take a core of sediment, and you slice it up, and you use carbon dating to see how far back in time you're going. And you look to see what years were sandy, what were clay, what might have had a certain sort of organism trapped in the sediment. And that gives you an idea of whether you had hurricanes, more overwash, whether you had more fresh water. That's another way. Tree rings, when you cut down a tree, count the rings, you look at how big they are, it tells you how much the tree grew in a certain year. And if you think of something like a redwood that can live for thousands of years, you take a current living redwood, you cut it, don't do this, but if it were cut down, you look at the rings, you can see what the weather was going back a couple thousand years. And even more so, many of you know that we have an underwater forest in the Gulf of Mexico. If you take petrified trees and do the same thing, you can go back tens, if not hundreds of thousands of years to figure out what the overall weather pattern was. It's not going to give you the daily weather. A couple other ways is looking at corals and also looking at pollen that's also trapped in sediment or even ice cores. So that's how we know what the weather was. And if you take, say, the last 100 years of ice cores and pollen and tree rings, you can calibrate it with a satellite, with a thermometer, with other weather instruments, and that's how you can go backward in time. So that's how we know. Also, old books, whether it's a religious writing or just a story of an occurrence going back. All right, so this is Mobile's temperature from last year, and a bunch of things are happening here. In the middle of that graph, there's a brown shaded area, and the brown shaded area is climate. It's the average low and the average high each day. And over that brown, you see that blue line jumping up and down. That's the actual high and the actual low. So remember I said climate is what you expect, but weather is what you get. And you'll notice most days the temperature is kind of within that climate area. And this is important because if you go back farther in time, there are multiple, here's one, someone had asked me on my page, has the Earth ever been warmer? Yes, it has been dramatically warmer and dramatically colder. This is all a science perspective. This graph goes back 500 million years, way before humanity. And what you see in red, if you can see the scale on the left, the temperature compared to what it is now, it sometimes was 30 degrees warmer, the average Earth temperature. And what you see in blue are the ice ages when it was, from where we are now, easily 10 to 15 degrees colder. So you use the proxies to go back in time, and you can pull this data out of that. So that's how we know. And by the way, we are right there. This is where we are at present time. So you'll notice they're cycles, up and down, up and down. They're not perfect cycles. Related to that, actually, this is kind of a cool graphic. See the people at the top of this graphic? This is modern day, but you can go back 2.5 billion years. And what I showed you about really hot, really cold, all that stuff, there were no human beings if you go back that far. So when you talk about climate change, it's not about that it never happened before. It's about it hasn't happened in the dramatic rate that it's happening now that we humans are on Earth and our societies are built. All right, so look at this map. It's just a map of the world. And on a glance, you might say, oh, well, North America is about the same size as Africa. On this map, it seems that way because of the map projection. So this is another thing that kind of throws people off. We say, well, it hasn't been warm in Mobile, therefore there is no climate change. Well, the United States, right there in the upper left, it is only 2% of the Earth's surface. 2%. And that sounds really tiny, but just remember, more than 2/3 of the Earth is ocean. So automatically, that's 66, 70%. It only leaves 30% land. But a map like this makes it appear that there's a lot of land. This one's a little better. These are NASA images, and it gives you a perspective of water compared to land. So 2/3 of the Earth, nobody lives there, but we do have sensors, satellite, buoys, that give us a really good idea of what is happening in those areas. All right, so what's climate change? It used to be called global warming. The globe is warming. The reason it's not really called global warming anymore is the globe is not warming evenly. It will not. Don't expect it to warm everywhere. Here's a bit of trivia on global warming and climate change. If you take a city and here's an example of climate change. A city, the daytime high, the average daytime high could actually fall 1 degree, but the nighttime low rises 2 degrees. That's warming, but it's not the warming you see or feel because most of us are not out at night. The climate change we're talking about now is human-induced climate change. So if you take normal climate cycles and you put the human cycles on top of it, it's like waves at the ocean because it's hard to pull them apart. But the trends are pretty clear. And the climate change we talk about now is, yes, the Earth is warming. The Earth is warming because a lot of we get our heat from the sun. The heat goes back to space, but we're putting more and more gases in the air that trap a lot of that heat. So we are retaining a lot of heat that used to escape. Point of trivia, the most potent greenhouse gas is water vapor. And that's a good thing. If not for water vapor, Earth would not be inhabitable. So a lot of times people want to confuse you and say, well, water vapor is the big greenhouse gas, but it's the other two I'll talk about in a minute. But if you look at this graph from NOAA, it's an energy budget. It shows shortwave energy comes in at a higher frequency, and when it's emitted from the Earth, it's a lower frequency, and it does all sorts of things in the atmosphere with the clouds. But the bottom line is we are warming. So what's the big deal? The big deal is not that climate is changing. The big deal is the fact that the rate of climate change in the last 150 years, since the Industrial Revolution, since our societies and our cities were built, the rate has never been higher. That's the big deal. It's going to impact, it is impacting our lives, commerce, transportation, agriculture, political. It has impact. And don't think, there was an old Twilight Zone episode, I think with Billy Mumy, the kid from Lost in Space, where the Earth was warming and warming, or maybe that was a different episode. But everything was warming, people were hot, they were sweating, they couldn't live. That's not what climate change is, at least for us. it's not like you're going to feel that it's 5 or 10 degrees hotter. It's all the things that ripple from the fact that the Earth is warming up. But infrastructure, health, and life, those are the big deals. And I think most people know it's fossil fuels that are chemically the issue. If you look at the chemical structure of CO2, carbon dioxide, if you look at the chemical structure of methane, CH4, you'll see that it matches the frequency of that long wave radiation. So basically, that's what kind of traps it. And that's really the shortest version of why fossil fuels are a big deal, because they are carbon. And the carbon meets the oxygen and it makes carbon dioxide. So, and as I'm talking, I'm trying to, this is the science, just again. So when you hear about climate change, there are some things that could happen. Actually, anything could happen. Anything could happen. There are two things you'll hear. One is called a positive feedback, and one is called a negative feedback. Although the negative one is actually positive for humanity. You heat the Earth, you get more, the Earth is warmer, more evaporation. It could create more clouds. And if you create more clouds, the clouds can reflect more sunlight back to space. So in other words, a negative feedback is, it stops what's happening. So a negative feedback would stop it or slow it. So that's a possibility. The other possibility, the one we hope for, is that plants and forests will thrive, and as they do so, they ingest, they take in the carbon dioxide. But unfortunately, there are more positive feedbacks, which are not positive. I'll show you in a minute. Here's the complexity of the water cycle. We don't know. This is an experiment that has never been done since we've been here. So we can hope that there are more clouds, but more clouds could mean more storms. And there are just so many moving parts to this. All right, so here are positive feedbacks. And remember that positive means it makes something go forward or progress. We know the Earth is warming. If you melt ice, you take away the shiny surface of the ice, the Earth gets darker and it absorbs more heat. So the more ice that melts, the faster the Earth is likely to warm. Positive feedback is methane, the methane that's trapped in glaciers, trapped in soil that is beneath ice sheets. As the ice melts, it releases the methane, and the methane is a very potent gas at trapping heat. That's not a good thing. And then right now, a lot of this is still, it's all in progress, but it seems right now that the warmer the ocean is, the less efficient it is at holding carbon dioxide. So we talk about weather maps, we talk about highs and lows, and the bottom line with climate change is as the climate changes, weather patterns will change. Exactly how, nobody can tell you. Nobody can tell you exactly how weather patterns will change, other than they're going to change. And remember, the big deal is we don't like change. So, you know, the west coast of the United States is cool, the east coast is mild. And that's because of the ocean currents, or gyres, which is how the ocean water circulates. And if you look at Greenland, and if you melt a lot of that ice on Greenland, you're putting cold water into the gyre, which is going to impact how much water circulates down to the tropics and back up the east coast of the United States. All things being equal, the way it is now, if you look at the warm water that goes up the east coast, the Gulf Current, and you look at the cold water that goes down the west coast, it brings this really important principle, and that principle is sea level will not rise everywhere. Sea level depends on how warm the water is. Right now, sea level is rising because the warm water is expanding. That's the main reason it's rising. But this is a graph, this is from NOAA. Go to tides and currents, just search for tides and currents, and it gives you real-time historical information of tide gauges for North America, Europe, parts of Africa, and you'll see that some parts of the world, sea level is falling. And it's based on local bathymetry, topography, and water density. All right, so these are just a half dozen scenarios of climate change. Sea level will rise in some spots, it'll fall in others. The atmosphere will be warmer, it'll hold more moisture, you will get more rain. You'll also get, and I'll show you why, more drought, and it doesn't seem that it's logical, but yes, you can have more rain in one region, more drought in the other. Growing seasons will increase, which sounds good, except longer growing season means more time for mold to grow, more time for insects to thrive and live, and it also means that some growing zones, for example, certain crops, coffee, for example, needs a really limited temperature range to grow. And as the zone shifts, the coffee farmers have to move. And it's not like you're moving from a house to another house, it's land. Populations, that will potentially be a big deal because of water resources and arable land or farmable land. In poorer parts of the country, as the weather pattern of the world, as the weather patterns shift, people will have to shift, and that's where you run into the political issues of migration. So some areas can get more snow. Just think about that. Yes, with climate change, a warming Earth, some areas can get more snow, simply because if you take an average temperature, let's say it's 27 degrees on average, and the climate warms to where it's 29 degrees on average, that little bit of warmer air allows more moisture in the air, which could fall as more snow. Yeah, it's all sorts of things that don't seem intuitive. The shipping lanes will open at the Arctic, but the melting ice, again, it's the issue of methane. What's that going to do? The question mark is extreme weather. How extreme will it be? Well, let's talk about the polar vortex. Jet stream encircles the Earth. This time of year, it's high latitudes. Some people call it the polar vortex. If you take the Earth and you warm it, the equator, the north and south poles will likely warm more than the equator because there's ice at the poles. And as they warm more than the equator, the jet stream is likely to slow down because the jet stream is driven by temperature difference. And if the jet stream slows, it may be more loopy. And when it loops, when it goes north, you get a heat wave. When it goes south, you get a cold outbreak. So again, doesn't seem logical, but that is a possibility with climate change. So here's the worst case scenario. The worst case scenario is the ice sheets that are on land melt, that we hit what's called a tipping point, which is known as the straw that broke the camel's back. We don't know what the tipping point is for how much warmer the Earth can be before that becomes really likely. But that is the worst case scenario, that the ice sheets slip off of land into the oceans, and then the oceans rise dramatically. So that's the short version. Make a quick analogy here. Here's the 7-day forecast. The forecast you heard yesterday is done. You have to listen to today's forecast to figure out the future. Tomorrow there will be an update. So all climate projections are going to be updated. And what's difficult about climate change is, unlike the 7-day forecast where I can tell you tomorrow how my forecast was, no one can tell you what the climate projections will be, because most of us will be gone. Most of us middle-aged people will be gone, which is not to say we shouldn't worry about it. Really look at the data. So much of it, I'll show you this quickly. You've heard about
2 minutes.
Carbon dioxide in Hawaii, Mauna Loa. It's at a level, this graph goes back just 40 years. This graph goes back 1,000,000 years. So that 40 years I just showed you, it's this part way on the right side of the graph. It is higher than it has been in the last 1,000,000 years. And it's directly using isotopes, which is flavors of carbon dioxide. It is directly from fossil fuel use. That's how we know. Also, quick question, how do we know it's not the sun? Well, there's a satellite pointing directly at the sun, and this is what it shows, is that the sun's energy has cycled a bit, but it's not going up, but our air temperature is going up. Unfortunately, I'm running out of time because we have a newscast starting, but I want to, and I may have to come back at 9 o'clock and finish this. If you have a climate question, and I can't answer all of them, go to this Facebook page. It's NASA Climate Change. And post your question, and a climatologist will answer your question. It's that simple.